Alright, we're going to look at temperature conversions this time around. So we have two learning targets for this section. You can distinguish what the difference between heat and temperature is. Though they're highly related, they do have some very important differences. And you can calculate between the three main types of temperature units: Celsius, Fahrenheit, and Kelvin. We'll get to those in a bit. Alright, so energy and temperature. Which of these have energy is the question. Do you think a ball in midair has energy? Do you think a book on the table has energy? And what about a book on the floor? Take a minute, think it over. Either out loud or on paper, write down what do you think. Which of these three have energy, and if so, what types? Okay, so ball in midair. Hopefully you said yes, it's got energy. It's got probably some kinetic one, unless it's at the top of its arc. And potential, if it's off the ground, it's got potential energy it can turn into and fall down. Okay? How about the book on the table? If you guys know your physical science well, if you've taken physics before, you'll know yes, it's definitely got potential energy. If it's up on a table, it can fall down. That's good. A book on the floor, a lot of you may have said no, it doesn't have any energy. However, if I were to say, alright, everybody freeze, and you freeze in some really weird pose, and ask you, do you still have energy? Your answer better be yes, even if you feel tired. You've got energy inside of you. Chemicals burning, making energy. You've always got atoms moving all the time. So the kinetic motion comes from those atoms bouncing around inside your body, doing things. Even when you freeze, you're not frozen. Even when the book is just sitting there, there's still atoms inside of it bouncing around and moving all the time. That makes a really big difference. So every single thing has energy. Always. Right, so temperature. Our definition, you might want to put this down, is a measure of the average, that's key, average kinetic energy of the atoms or molecules inside it. So some might be going faster, some might be going slower. They almost definitely are. We're looking for the average of them. So when the temperature goes up, that means the overall energy for most of those atoms on average is going up. Some of them may stay the same, some may go down even, but on average, those particles are moving faster as they jump around. So it's like a slow one means it's a cold object. As they start having a higher temperature, that means they're moving faster. This faster movement causes a higher temperature. That's a higher average speed of those atoms or particles. Right, so then why do grains of sand seem to stand still if they've got all this motion in them? Well, even as small as grains of sand are, they're so much larger than atoms are. The atoms inside of them are millions and millions and millions of times smaller than one grain of sand. So we can't see the motion of the atoms because they're far too teeny inside of those grains of sand, but they're still moving. Alright, then heat and thermal energy. Click. Alright, so heat on the other hand, oh, we don't want that. Go ahead. Okay, heat on the other hand, it's our total amount of kinetic energy in a substance. So it's not the average, it's not some are higher, some are lower, whether they're high, low, or the average. We take the sum, the total of all those particles, all that movement, add together. That's going to be your heat. All of them added together compared to the average. So both heat, any kind of energy, is measured in joules, usually, sometimes in calories. Now this calories are not quite the same calories as you get in your food. Technically those should be kilocalories. So you put a little K in front of this C. Technically you're eating 1,000 little calories of energy every time you eat 1 calorie of something. So technically if they say you need 2,000 calories in a daily diet, you technically need 2 million real calories, or 2,000 kilocalories. Note that a joule is a relatively small unit of energy. Because if you take 100 milliliters, which is like, I don't know, that much water. Yep, go back. And you take it from room temperature, and you boil it, it takes over 33,000 joules to make that happen, which means there's a lot of energy going in there, but each joule is not much. We usually say 33,000 or 33 kilojoules once we get above 1,000 joules. All right, think, pair, share. Which if you're by yourself, then just take a minute, think this over, see what your answer is going to be and why, then we'll go through it. So which has more heat? A hot cup of coffee or a bathtub of water at room temperature? So pause, think about it, then when you've got an answer, hit play. The best way to learn it. Okay, so this next slide. The bathtub, if we can read this, the bathtub has far more energy because it has more mass. Because remember, the temperature is the average amount, so on average, that coffee cup's got a way higher temperature. But if we're looking for the total heat, the total energy, even if those particles in the bathtub have a half or a fourth of the energy of the coffee cup, there's so many more particles. When you add them all together, it's going to have a way, way higher amount of energy than it does in that coffee cup. Hopefully that makes sense. Here's another way of looking at it. Oh, get my face out of there. So imagine there's a jar with particles in it, and each of these particles has a different amount of energy. We'll denote them by the numbers on these octangular, or many-shaped particles. Now, heat is measuring our total energy, like all the energy in that bathtub, all the energy in that coffee cup. To find the heat, we add up all the numbers. So all the 1s plus all the 2s gets us a total heat amount of 12. Whereas with the temperature, we're measuring the average. So we add them all up, then divide by how many particles there are, which means we've only got a temperature of 1.5. Now we have no units on here because it's an odd, very simplistic scenario, but the heat is way higher than the temperature is. That's almost always going to be the case. Because you're summing them up versus averaging them. You have to divide it for temperature. You don't for heat. It's just the total. Okay. So heat and temperature are not the same. They are closely related, but very much different. Make sure you know the difference. It'll come back to you in a quiz or test in this unit. Okay, our temperature scales. There used to be a bunch. Technically they still exist, but the world really only uses 3 of them these days. Us in the US uses Fahrenheit, and we're one of the very few countries that still does. In our case, most of you know that water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. The most common one is the Celsius scale. It's used almost everywhere in the world. In their case, their numbers are easy. Water freezes at 0 and boils at 100 degrees Celsius. Then the last one we need, which we'll use a lot with this gas law stuff, and use a lot in science, is the Kelvin scale. So Kelvin, water freezes at 273 Kelvin, and it boils at 373 Kelvin. Do you note a pattern between the Celsius numbers and the Kelvin numbers? They seem to be off by the same amount every time. How convenient. So Kelvin is based on something called absolute zero. It's the lowest temperature possible. That's the point at which atoms have no kinetic energy. We haven't technically gotten there. We've gotten really, really close, like 0.00000000000001 Kelvin. That's really, really cold. But technically there's still movement there. Okay. Now note, in all those things, when we talk about Kelvin or Kelvins, there's no degree sign. There's degrees Fahrenheit, degrees Celsius. It's just Kelvin or Kelvins. So water boils at these amounts, freezes at these amounts, and absolute zero, that point of no motion whatsoever, no atomic motion, would be at these different numbers. It's very important that we have no negative numbers in Kelvin when we get to the gas laws and do some math with it. Just beware. Okay, let's do some converting. So, formula, you want the temperature in Kelvin. That's what we're looking for. then we have to know the temperature in Celsius, and we just add 273.15 technically. The Celsius is the exact opposite. If you know Kelvin, just subtract 273.15. I believe only one of these is on the back of your periodic table. You may want to check which one, but it should be pretty easy to flip-flop and solve for the other variable. So let's say you have a pen pal from England, and he says he's going for a run outside because it's 230 Kelvin. What would that be in Celsius? Well, we got to do the conversion, got to do the math. So we know we've got Kelvin, he's asking Celsius. Because of that, we want to choose this bottom one where it's solving for Celsius. We'll put in our Kelvin temperature here. So we'll take 230 Kelvin minus 273.15, and we're going to get about negative 43 degrees Celsius. Does that seem reasonable? He's running outside when it's negative 43 degrees Celsius. You guys may not know this, unless you're familiar with Europe or the Celsius scale, centigrade scale. But that's really, really cold. It's like the coldest days we ever have in Minnesota. So no, it's not reasonable. He should not be running at that temperature. Okay, let's say I'm running an experiment with liquid nitrogen, which is awesome. It freezes things so quickly. And obviously it's at negative 196 degrees Celsius. What would that be in Kelvin? So now we're looking for Kelvin, so we're going to use this top formula. Plug in the Celsius temperature of negative 196 plus 273.15, and we'll get our temperature in Kelvin to be 77-ish Kelvin. We apparently didn't add the 0.15s in there, but probably should. Okay. So just note which ones are on the back periodic table, which ones are not, so you need to know them or how to get them, solve for them. Alright, let's do the trickier ones. Fahrenheit and Celsius. Also looking back periodic tables for these, I think you get one and not the other, or it's missing parentheses. Remember, parentheses work the same way in science as they do math. Science is just applied mathematics. So you must do everything that's in the parentheses before you do the other stuff. So you have to take 9 divided by 5 times the temperature in Celsius plus 32. Or the Fahrenheit temperature minus 32 first, then multiply by 5/9. Makes a huge difference in your answer. So your pen pal from England's back. Since it's 34 degrees Celsius, what would that be in Fahrenheit? And you blokes in the US? Well, let's find out. Let's take our 34 degrees Celsius. They want Fahrenheit, so we'll use the top formula. Plug 34 in here, times 9/5, then add 32. We should get 93.2 degrees Fahrenheit. That's nice and warm. A little bit of sweat coming down. Now he says, if he asks how cold he gets in Minnesota, and we say, yeah, negative 40 degrees Fahrenheit, but he wants that in Celsius, we need to convert it back. So we take our Fahrenheit temperature, put it in here, minus 32 from it, and then multiply by 5/9, and we get an answer of, what? Negative 40 degrees Celsius? Yep, there's one temperature where the Fahrenheit scale meets the Celsius scale. It's at negative 40 degrees. So if you say it's negative 40 degrees out, it'll be the only time I don't require to use a unit because they're the exact same. You can't have negative Kelvin, so that's why. Oh, there we go. All right, let's do one or two a little bit harder. It'll be done. Your teacher tells you it's going to be 290 Kelvin outside today. What would that be in Fahrenheit? So you have to go from Kelvin to Celsius, then over to Fahrenheit. It's going to be a two-step problem. You should get 16.85 degrees Celsius in your middle step. Now go to Fahrenheit, or you should be pausing, trying these, and then seeing if you get the right answer or not. When you go to Fahrenheit, you should be getting 63.33 degrees Fahrenheit. Hopefully you got that. If so, do this next one, we're good to go. If I then tell you it's negative 34.5 degrees Fahrenheit outside, what would that be in Kelvin? Again, it's two steps. Fahrenheit to Celsius, then Celsius to Kelvin. Hopefully you get an answer of 236.21 Kelvin. If you got that or really close, say, hey, you get it? Awesome. We can move on and do some gas law stuff. See you next time.